Hi, we're Group 21. I'm Derek Zeal.
I'm Kyle Brown.
I'm Anna Koch.
I'm Kyle Lake, and our senior design project is the MPPT charge controller.
During optimal operating conditions, solar panels produce an output voltage that stays within a limited range. This is fine when power is fed back to the power company, but not very efficient if you're trying to charge a battery with a solar panel. A charge controller can be used to more effectively utilize the power being produced. To improve the functionality of a charge controller, you can implement a maximum power point tracking charge controller, or MPPT. An MPPT charge controller adjusts the load presented to the solar panel in order to utilize the highest power production possible by the panel.
Now we'll look at our block diagram to see more details of how this system is integrated. There are three main paths in the system. Shown here is the main flow of power. The DC to DC converter requires there to be isolation between the primary and secondary sides of the system, meaning that the ground on the first side is different from the ground on the secondary side. The microcontroller is located on the primary side, so in order to send sensing measurements from the secondary side back to it, we had to implement opto-isolator circuits. The low power path is shown in red. The blocks of our system are powered by either 5 volts, regulated from the input by the voltage regulator, or regulated 3.3 volts from the microcontroller. The final path is the flow of data and logic through the system, shown in blue. This encompasses all data flowing in and out of the microcontroller.
Let's look at how the power flows through the main operating points of our system. The panel is connected to the input side of our system. A button and relay is used as a locking mechanism, which can unlatch to entirely cut power to the system. A 5-volt regulator is attached to convert a portion of the input power to 5 volts to operate the system. Next, the power from the panel encounters a series of sensing circuits. The voltage and current sensors measure the input power to provide data to the microcontroller so that appropriate outputs can be sent to control the system. The current sensor requires a reference voltage taken without current flowing through it. To implement this, we use a relay to divert the current path from going through the current sensor. A temperature sensor on the evaluation board for the microcontroller is used to monitor the internal temperature of the enclosure. The third relay on the input side of the system is for overvoltage protection. When a voltage at the input is above 40 volts, this relay opens the current path and cuts power to the secondary side of the system.
After leaving the relays, the input power travels to the DC to DC converter. The DC to DC converter is able to adjust the output power by stepping down the voltage. This new output power then travels through the secondary voltage sensor, current sensor, and relays, which are implemented similarly to the primary side sensors. The values are used by the microcontroller in the perturb and observe algorithm to track the maximum power point. The power then exits our system to charge an external battery. A final sensor is placed on the battery to monitor battery temperature and maintain safe operation.
In order to introduce a variable load to the solar panel, we use a DC to DC converter which manipulates the output voltage of the system. A digital potentiometer controlled by the microcontroller varies the output voltage of the DC to DC converter. Our converter bucks input voltages to a range of 12 to 15 volts, which is acceptable for charging a 12-volt battery. It has an average efficiency of 80%, and so is the main source of loss in our system.
To track the maximum power point, we use a perturb and observe algorithm. The microcontroller receives input from the sensing circuits and varies the output voltage accordingly. If the input and output power increase, the system should adjust the voltage in the same direction, but if the input or output power decrease, the voltage should be adjusted in the opposite direction. It was required that our system could handle a high amount of current and voltage. Our system was able to meet the requirement of outputting 150 watts. In order to reach a maximum power point with a degree of precision, it was required that our system could accurately change the output voltage of the charge controller. We were able to manipulate the output voltage with a 100 millivolt resolution and meet the system requirement. Since we are dealing with a potentially dangerous power, safety is an important part of our system. Our enclosure is finger safe, which keeps small objects from reaching the circuits from the outside. It is protected from objects 12.5 millimeters or wider. Our enclosure is also water resistant from 3 millimeters of rainfall for 10 minutes while it is tilted at a 15-degree angle to protect the electronic components. We were able to meet this requirement. Our system should be user-friendly. Our display is readable from at least 2 feet away, outdoors, during daylight hours. Given that we were utilizing an inexpensive LCD, it is possible that this would have been difficult to see in the light, which is why we chose a backlit display.
Unfortunately, our system was unable to meet all 10 of our engineering requirements before the final checkoff. System integration required much greater time than was available in order to get the system operating correctly. Because of these constraints, we were unable to meet some of our requirements. In our design, it was possible that our circuits could reach excessive temperatures. Because of this, there were 2 temperature requirements which were meant to keep our electronics safe. If the battery temperature exceeds 45 degrees Celsius, the current supply to the battery should be cut off. Also, if the internal temperature reached 60 degrees Celsius, the system should shut down. Our system incorporated mechanical relays in order to perform these functions. These relays proved to be very problematic to use. They interfered with our communication between system devices. This was a problem that was unable to be solved before final checkoff. Similarly, our system should have been protected from overvoltages. This was also being implemented through relay control. In a charge controlling system, it is important that our system does not harm the battery being charged. If the charge controller continues to charge a battery when it is full, the battery could become harmed and could possibly become dangerous. The engineering requirement was that if the charge level of the battery reached 90%, the output current will be lowered to a trickle charge state. In order to implement this, we plan to monitor the current on the output of the controller and use the current measurement to calculate the charge. We had the ability to do this, however, we were unable to integrate the secondary current sensing circuit. Our system also needed to track the power from the solar panel over a range of light intensities, with the system representing a load to the panel within 20% of the cell's maximum power point. When attempting to demonstrate this requirement during our final testing, we damaged the voltage regulator because the panel voltage was too high and we were unable to test this functionality. We're Group 21, the maximum PowerPoint tracking charge controller, and one of our requirements was that our charge controller can output 150 watts. So this is the 150 watt test. We have our power supply set up to 36 volts, and which is input to this side of the charge controller. And then on the output we have a dynamic load that we will load the charge controller to 150 watts, approximately 10 amps. The DC to DC converter is nominally at 15 volts. So I'll turn it on. Our system turns on and we're at 34.8 volts on the input and 34.81 volts on the output without load. I'll start the load at half an amp. And slowly increase until we get to about 10 amps. About a third of the way, we're at 3.8 amps and 51 watts. About 2/3 of the way, we're at 8 amps now. We've reached 150 watts, and that concludes our test.
One of our requirements is that our circuits will be protected from the elements. So here we have it set up to emulate rainfall to show that it's water resistant. We have it tilted at a degree of 15 degrees in order to show rainfall coming from the side. So I've got this watering can and I'll pour the water over it for a few minutes. So now I will dry it off, and so we can inspect to see if there's any water inside the enclosure. So as you can see, there's not any water inside the enclosure, and our circuits are protected from the elements.
So this test will demonstrate that the system is safe to use. At about 150 watts at 10 amps, it can potentially be dangerous. So this test will demonstrate that the system is not accessible to objects 12.5 millimeters or larger. I have here a pencil, which is clearly smaller than somebody's finger. As you can see from all sides, the object can't enter the enclosure, including the bottom. So the system is completely safe to any user.
Finally, we'd like to offer some advice for future seniors.
My advice would be to always have a backup plan. From components to testing, it's rare that a portion of the project works the way you expect it to the first time. It's important to always have something in mind that you can try next if your current approach doesn't work.
My advice is to choose a project that you will enjoy. You'll be spending more hours working in the lab on your project than you want to keep track of. So enjoying the project will help keep you going.
My advice is to get a mentor that is knowledgeable about your specific project. There are many times when we had no idea about the parts of our system and were dealing with problems far beyond classes we had taken. It would have been very helpful to have a mentor who had more knowledge about these kind of systems that we could ask questions.
My advice is that you shouldn't underestimate your project. Going in, I expected our project to be a lot easier than it was, and I was sadly mistaken.